Alrighty, folks. Let's move on here to lesson 3. We're going to talk about inverses of relations. This is going to kind of wrap up topic 1 of our first unit. So we can kind of think of this as almost like the halfway mark, although it's actually a little more than half of the unit in terms of number of lessons. Okay, this is going to kind of wrap up the operations portion, and then in the next lesson we'll move on to the transformations portion. So after this, if you want to do your topic 1 quiz, check-in, whatever you want to call it, you'll be good to go once you've practiced this material and feel comfortable with it. And as always, reached out to me with any questions or concerns you had. Okay, and again, as always, little checklist you can kind of use, right? The big ideas that we're hoping to come away with after this lesson. Again, okay if not, but lets you know, all right, I need to review that. I'm not quite sure I'm comfortable with that skill just yet. All right, well, let's jump in. So, we're going to be talking in this lesson about inverses of functions. Okay, we've been talking about functions quite a bit. We're going to talk about taking their inverse. Now, before we do that, we're going to have to remind ourselves of an overarching concept here, okay? And that is the concept of a relation versus a function. I shouldn't say versus because really functions are relations. This is something we talk about more so in Math 10C. It comes up a little bit in Math 20, okay? But relations, I mean, it's kind of the clue is in the name, right? A relation is really, it's a relationship between two things, right? It's something that essentially connects one value to another. It's like a rule that shows you how one thing depends on another. Doesn't that sound a lot like a function? It should, because a function is actually a type of relation, okay? We've looked at functions where here's how y depends on x, right? Maybe y is equal to the x squared, or y is equal to, the square root of x over 3, whatever it might be, okay? Usually we're looking at how, x and y are connected. Those are just two names we like to give to variables. It's showing the relationship between an x and a y, two different variables that might depend on each other. So they often show, as we've seen, how y depends on x. So like I said, functions are relations. They're just a special type of relation. Okay, they're a specific type of relation. It's kind of like, how all squares are rectangles, but not all rectangles are squares, right? Kind of same idea here. All functions are relations. There's just some relations that aren't functions. This diagram here kind of gives a good idea, right? Functions are relations, but there are other types of relations which cannot be classified as a function. So what makes it a function? What does it have to have? One key characteristic makes a relation, a function. And that is that each input value, right, what we would typically call x, okay, corresponds to only one output value. That's what we would typically call y, right? So whenever we input an x, it should only ever give us one output. We can't get two different y's from one x going in, okay? So all functions are relations, but not all relations are functions, like we talked about here, okay? Now the key characteristic, again, of a function is that it has only one output, one y, one f of x value for each specific input, our x's that we're actually going to put in, okay? So for example, just to look at a couple, visual mappings of these functions, this one is a function, right? A specific input, a specific x, only ever leads to one specific output, y, right? So like 2 became 4. It's not like 2 could sometimes give us a 6, right? 2 only ever gave us 4. 3 only ever gave us 6, 4 only ever gave us 8. When we input these, they map to one specific output, okay? Now, notice what I'm saying there. One input only ever gives us the same specific output. This is also a function here because, again, 2 is giving us 4. And so is negative 2. Negative 2 can also give us 4. This is still a function. In fact, this is actually the function. I mean, it looks like the function anyway. F of x equals x squared, right? Because if I square 2, I'm going to get an output of 4. If I square negative 2, I'll also get an output of 4. Okay, so this is a function. Whoops. This is a function because a specific input is still leading to only one output. That's the key. 2 is not giving us, maybe 4 or 9. 2 is only ever giving us 4. It's just that another input is also giving us an output of 4. So note that it's still a function if multiple inputs result in the same output, as long as one input doesn't result in multiple outputs, right? I know that's a bit confusing to follow along with, okay? But to see a non-example might help clear things up. This is not a function. Okay, it is still a relation. There's still a relation between these inputs and these outputs, right? The 4 is related to these things. There's a set of rules that shows how this relates to these outputs, okay? But it is not a function because one input is leading to more than one output, right? Remember, we often use that analogy of a function being kind of like a machine. We input stuff and it outputs something, right? It's a good machine. It's a consistent machine. Whenever we put in a 4, if it's a function, we should always get the same output, right? This is a function. No matter what I put into x, right, I'm always only ever going to get that one output. It might be a different output when I put in different x's, but it's not like I could put 1 into this function and sometimes get out a 1 or a 2 or a 3, right? I know when I put in a specific x, I will get out a specific y, right? Okay, so this is not a function. Still a relation because it is still a relationship between two variables, right? But it's not a function because a specific input is leading to more than one output, y, okay? Now, we're reminding ourselves of this because we're going to be talking about some inverses of relations which sometimes are not functions. They're still relations, but sometimes they are not functions, okay? And so before we move into doing that, we'll just remind ourselves of something because we're going to want to be able to tell today sometimes if something is a function, or if its inverse will be a function, or given the inverse, tell if the original was a function. We want to be able to know whether something's a function or not today. That's often something we're interested in, or how to make it a function if it's not, okay? So with this in mind, we can visualize the features of the graph of a function, right? Start thinking about that. What does that mean? What would the graph look like if each x only ever gives us one specific y, right? If you look ahead a bit here, you can start to think about which of these graphs looks like a function, which one only ever gives us one specific y value at each individual x value. Well, we make use of something called a vertical line test, okay? Because again, for each input, each x, we should have only one output, y, right? At each x, we should only ever have one y. One x can never give us 2 or more different y's, right? That's the whole point of a function. Again, different x's could give us the same y, but one x can't give us different y's, right? One input should always lead to the same output. 2 does not sometimes give us 9, right? It always gives us 4, okay? So that's why we can use something called a vertical line test to check. It's basically, it's what it sounds like. It's a test to see if something is a function or not. And it's a very, very simple test. Here's what we're going to do. You can actually draw it, or you can even just picture it, right? Draw or imagine a vertical line going through your graph at various values of x. And if at any point, if there is any single place you can find, any single x value that you can find where the vertical line intersects with our graph more than once, then that graph is not the graph of a function. It can't be, okay? Which makes a lot of sense when we think about it, because what are we doing by drawing a vertical line? We're just examining a specific x value. We're essentially checking, right? If I were to draw a vertical line here at x equals 1, right? What I'm essentially doing is looking, okay, does that graph ever intersect with that line when x is 1? Is there more than one y value for the graph, right? Because if there is, this can't be a function, right? I mean, you can kind of see here, at this location anyway, it passed the vertical line test. At x equals 1, there is only one y output that we can see on the graph. It happens right there, okay? So more than one intersection with that line would mean the opposite. It would mean that there was more than one y as the output of that individual x. So that's all we're doing when we draw a vertical line. We're examining one specific value of x. And so if we can do that kind of everywhere, imagine drawing the vertical line everywhere, then we are testing to see, are there any points where one x input gave us more than one y output? Because if so, it's not a function. So if no matter where you put the vertical line, it only intersects with the graph once at most, then the graph is a function. Okay, so I know sometimes in younger grades they call this the pencil test, because you imagine taking a pencil and holding it like this. If you were doing it on paper, you hold your pencil and you kind of slide it around and see if you can make the pencil touch the graph more than once. Okay, let's make use of the vertical line test here, right? So if I were to draw, you can probably tell right off the bat, this one, not a function, right? Very easy to imagine a vertical line that intersects with our graph more than once, right? And again, we can tell this is not a function because look, when x is -10, our function is giving an output of 20 or an output of -10. Two different y outputs for the same x input, right? That's not what a function does. When x is -10, if it were a function, it should just be giving us one consistent output for y, right? Not two different things. Basically, we should know what we're going to get with a function when we put in an x, okay? And there we don't. There's two different possibilities, right? There's a million places you could draw and see that this fails the vertical line test all over the place. Let's take a look at this next one here, kind of a funky looking graph, one that we'll look at ones like this in Unit 2. This is the graph of a polynomial function, okay? But this looks pretty promising to me, right? I'm imagining taking a vertical line and sliding it across, but even if I actually draw them in, right, you can see at each x, and again, what I'm examining by drawing a vertical line is different x values. Like right now, I'm examining x equals -1. And no matter where I draw it, it seems like I'm only getting one y value, right? One intersection here. Because that's showing me now, or what that's showing me now, is that at all of those x's, there's only ever, at most, one y output, right? So that fits the definition of a function. Okay, so I could say this one is a function. So function, right? Not a function. So far, those two down, two to go. Okay, this one, what do you think? Try out these next two. Pause the video if you want, work ahead of me, right? What do you think? Okay, well, this just looks like a linear function, right? I kind of gave it away there, I guess, by calling it a function, but, right, look what I mean. Draw vertical lines no matter where you want to draw them, right? You could sit here all day and draw vertical lines, examining specific x values, and you'll notice that our function never gave us more than one y value, right? At x is 5, we just got y being 1. Not y being 1 and sometimes something else, right? At x being -3, we just got y being -2 point something, right? Not two different y values at that x value either. So no matter where you draw those vertical lines, you are not getting more than one intersection. This looks like a function. And you can probably tell here, right? Is this ellipse, we would call this, is it a function? No, right? Look, pretty easy to find a place where it intersects more than once, right? If you were not looking at the whole picture and you just drew it there, you might say, okay, but don't forget, right? If anywhere you can make it intersect more than once, it cannot be a function. For all values of x, if something's going to be a function, it should not intersect with a vertical line more than once. Because again, vertical lines are just examining one x value. So this one, not a function. Okay. All right, so there's our little reminder of what a function is. Again, bringing it up because today we're going to look at stuff that, might not be a function, and we want to be able to tell when it is, when it isn't, and what we would need to do in some cases in order to limit our domain to make it be a function. That'll hopefully make sense as we go through and see some of the stuff we're talking about. But let's move into the main focus for today, which is the inverse of a relation. Okay, so an inverse relation essentially reverses another relation. Okay, if we have, the cool thing about the inverse of a relationship is that if we can, if we have one relation or one function and we know its inverse, the inverse essentially undoes the original function, right? So, I mean, just for one example, if we had y equals x squared, right, what this does is it squares x's and it gives us y's. Okay, the inverse function of that, we'll actually find this one today. The inverse function of it would be this, plus or minus the square root of x. Okay, now hopefully you can kind of see what I mean. If I put x's into this function, they get squared, right? So if I were to take the outputs of that function and put them into its inverse, what would it do? It would square root them or unsquare them, right? Just for an example, let's say I put 2 into this function. If I put 2 into x squared, I get 4, right? What the inverse of the function can do is take the outputs of this and undo whatever this function did and get us back to our original input. So sure enough, if I do y equals plus minus square root of 4 now, right? Take the output of that and put it into this function and it should undo it. I get plus or minus 2. I know that my original input was the plus 2, right? But it could have been negative 2. I would have gotten the same result. If I had put negative 2 squared in, I would have got 4. That's why that plus minus is there, to make sure we find both possible, values here that are the square root of 4, okay? So big picture, that's what the inverse of a relation or the inverse of a function can do. That's why we call it the inverse. It undoes another function, right? An inverse relation puts another relation into reverse, right? We took y equals x squared, that squared 2 into 4. Its inverse relation took that 4 and unsquared it back into 2, okay? So how do we get that? All we actually have to do to come up with the inverse of a relation is swap x and y. So the x and y coordinates are just switched for the inverse of a relation. That actually makes a ton of sense when you think about it, because x and y, that's our input-output. Since the inverse of a relation reverses that relation, we want to take what used to be our, input gave us an output. We want to be able to turn that output back into the original input we had. So our new output should be the original input, right? See what I'm saying? Our new y should kind of be our original x, and vice versa. Our new x should be our original y. When we take the inverse of a function, that's what we want to do. We want to swap x and y. Old output becomes new input. So we literally do that. We literally swap each y for x and each x for y. Now you can probably reason, and we'll see this in action today, that means since domain is the set of all valid x values and the range is the set of all valid y values, if we switch what's x and what's y, we're going to end up switching the domain and the range. When I go from a function to an inverse function, okay, the original domain will become the inverse's range, and vice versa. The original's range should become the inverse's domain. So the graphs of a relation and its inverse are reflections of each other in the line y equals x, because of the fact that x and y are getting switched. That might not be super obvious right now that it will be a reflection in that line. When we take a look at some graphing examples, hopefully I'll be able to convince you that it actually does make sense that when we take the inverse, when we swap x and y, it ends up just being the same as if we had reflected that graph in the line y equals x. We are also going to talk a lot more about reflections in the upcoming lessons on transformations. That's one of the transformations we're going to do to graphs. We're going to reflect them, okay? But just for now, let's focus on how this can be represented, okay, symbolically. We take the inverse, taking the inverse of a relation can be represented in a few ways. One, hey, look at this. We're used to saying y equals f of x. If we want to take the inverse of a function, right? If I want to take the inverse of y equals f of x, this is how I could represent that. I would say I'm gonna write the equation for x equals f of y, right? Notice, literally x and y changing place. We also sometimes use this one. This one can throw students off sometimes. This is not saying to the power of -1. This is like, hey, remember sine, right? Sine of theta equals whatever, right? What did we call this? if I took the inverse sine of something, that would give me theta, right? That's because we called this the inverse sine. Remember that, right? And what does it do? It reverses the sign, right? If I knew that sine theta equals, opposite over hypotenuse, right? And maybe I know, say I knew opposite over hypotenuse and I wanted to figure out what the angle had to be, what would I do? I would take the inverse sine. Notice how these kind of undo each other, right? If I know the angle, I could take the sine of the angle and get the ratio opposite over hypotenuse. If I know the ratio opposite over hypotenuse, I can take the inverse sine and get myself the angle, right? Doing sine of this will give me that. Doing the inverse sine of this reverses the function. It gets me back to the angle, okay? So that is actually a perfect example of an inverse relation. That's why we call it inverse sine. But anyway, that's what that -1 is saying there. That's just saying the inverse. We don't have to put something to the power of -1 or anything like that mathematically. That's a symbolic way of representing we're taking the inverse. Just an important note here, we should technically only use this notation if the inverse relation is itself a function. Okay, we're going to see ones today where the original might be a function, but once we take the inverse, it is not a function. Okay, so technically we should only use this symbol. This symbol is this symbol, this way of representing it. If once we take the inverse, it will also be a function, right? In other words, if the graph of the inverse would itself pass the vertical line test. Okay, so again, if we had like a parabola, it's going to end up, spoiler, it's going to end up looking like that. Okay, so technically we shouldn't use that terminology for if we were taking the inverse of a quadratic function, for example, because the inverse would not itself be a function, right? Or we can also use what's called mapping notation, which we will see a lot of in the coming lessons. This just basically shows what's happening to every point. And this is literally what's happening to every point. The x value and the y value are getting swapped. Y ends up in x's spot, x ends up in y's spot, okay? So the inverse of a relation can be found algebraically by just literally look at the equation, look at where x and y are, then switch them. And then since we want to write an equation in terms of y, our dependent variable, we'll just have to isolate y, right? Do the opposite of whatever's happening to it until we've isolated y. Undo the operations being performed on it, okay? Or graphically, we can swap the x and y coordinates of each point, right? If I see the point on my graph, 2, 1, I'll switch it to 1, 2, and I'll graph my new point, okay? And as we'll see when we get into some graphing examples, this ends up being the same as reflecting the graph in the line y equals x. All right, one more thing we'll talk about here before we get into some examples, and that is a reminder of this term, an invariant point. It's a good name because it tells you what it means, right? It doesn't vary. It's a point that doesn't vary. Vary as in change. It's a point that does not change, okay? It's an invariant point doesn't change its location when some transformation is performed on the original function or relation. We're going to see lots of different ways we can get invariant points in this course. Okay, here's one of the first ones we're going to take a look at, okay? But since we're taking the inverse of a relation, that just means what we're doing is we're swapping x's for y's. So if you think about that, what kind of point would not change if we switch the x and the y value? Because that's where we're going to have invariant points, right? Invariant points are just points that you do something to the graph and that point actually wasn't affected. It still stayed in the same spot. Well, if we think about that, right, if I switch x and y and the point didn't move, that's only possible if x and y were the same thing, right? So the invariant points for taking the inverse of a function, they're the points where y and x were already the same thing, right? So for example, if a function had the points 1, 1, 3, 3, and -10, -10, right? If I switch those, is that point actually in a different place now? No, right? I still took the inverse, but it didn't vary the point. The point is invariant to that transformation or that operation of having its inverse taken. Still in the same spot. So all three of those would be invariant if we took the inverse, right? For some non-examples of invariant points, none of these would be invariant, right? The point 2, 3 is not the same as the point 3, 2. Right? If I switch these, that's now in a different location. Same for these, careful with the negatives, right? Negative 3, 3. If I swap x and y, well, 3, negative 3 is not in the same place as negative 3, 3, right? 5, negative 5, same story. All of those would not be invariant if we took the inverse, because again, switching their x and y's would give us a different point. Negative 5, 5 is not the same point as 5, negative 5. Alrighty, so let's try out some examples. Now, don't overthink this, folks. We really are. If we want to find the equation of the inverse for these, what we have to do is swap x and y. And that's really all there is to it. I mean, we'll swap x and y, and then we'll solve for y to get the actual equation of the inverse, okay? But again, because an inverse essentially reverses a relation or a function, okay, we want to swap output for input so that, you know, old output becomes the new input, and that gives us the original input as our new output. I know that's a little bit confusing, right? But we're swapping y and x so that what used to be our output can become the input and give us our new output, which is actually the original input. I confused myself there with that sentence. All right, swap x and y. That's what we're going to do, okay? Let's not overcomplicate it. So y equals x plus 3. Here it is, ready to take the inverse? If y equals x plus 3, then the inverse is x equals y plus 3. There we go. We took the inverse. Now, we don't have the equation of the inverse because, you know, an equation we would typically want to graph it, or we might want to graph it. And in order to do that, we need to isolate y, right? We usually graph stuff like not x equals y plus 3, but y equals x minus 3. So in order to isolate y, right now it's having 3 added to it. So in order to undo that operation, I'll subtract 3 from both sides, and I'll get x minus 3 equals y. And usually it just, you know, feels better to put the y on the left side there. So y equals x minus 3. That's the inverse relation for y equals x plus 3. That's it. Okay, let's do this one. F of x equals 3x plus 6. I mean, we know f of x means y, but I might just, you know, write that in so we can really see it. And here's what I'm going to do. Ready? I'm going to swap x and y. Wherever I see the x, I put the y. Wherever I see the y, I put the x. So this means for the inverse, x equals 3y plus 6. And now I just need to isolate y. Okay? So again, manipulation, right? Reverse order of operations because we're undoing the things that are happening to the variable we want to isolate, right? We want to isolate y. Right now it's not isolated because there are operations being performed on it. It's being multiplied by 3. It's having 6 added. And since we're going to undo those, right? We're going to undo those operations in order to isolate y. That's why we work backwards through the order of operations. So it's having 6 added to it. First things first, let's subtract 6 from both sides in order to undo that. So we get x minus 6 equals 3y. And then y is being multiplied by 3. So in order to undo that, the opposite of multiplication is division. In fact, we call that the inverse operation, right? Connecting back to today's lesson, right? The inverse operation of multiplication is division because division undoes, it reverses, so to speak, multiplication. Okay, so this gives us y equals x minus 6 over 3. Nothing wrong with that, but typically, you know, it's nice to write things in the form for a line. You might recall y equals mx plus b. Why is that nice? It just makes it really good for graphing because we can see the y-intercept right away. We can see the slope, okay? So technically we have written the equation of the inverse, but if it were me personally, I might just rewrite this as x over 3 or 1/3 x minus 6 over 3, right? Just essentially splitting this up, right? So this is, here, sorry, let me just show my work a little bit more there. I might just write this as x over 3 minus 6 over 3, basically splitting that up. And then to really write it in y equals mx plus b form, this would be 1/3 x minus 2, okay? Again, is that mandatory? No, but it's nice to have lines in that y equals mx plus b form whenever we have the equation of a line. So y equals 1/3 x minus 2. Ran out of room a little bit there, my apologies. Alrighty, Moving on, the option C here, or question C, okay, y equals x squared. We want to take the inverse, so what am I going to do? X equals y squared. And now to isolate for y, we have to do the opposite operation of squaring. Well, that is square rooting. Square rooting is the inverse operation of squaring, right? It undoes squaring. So let me square root and square root. Now we've got to be careful here. We took that square root, right? We took it. It wasn't part of the equation. If it had just been part of the equation, then they would need to write in the plus minus if they wanted us to consider both. But the square root of x is actually not just square root x in this case. We have to specify it could be plus or minus. Why? I mean, to get at that, right? If we have a 4 and we want to take the square root of it, okay, so there's a 4, we want to take the square root, we have to be aware that there's actually two options. The square root of 4 could be 2, because 2 squared is 4, right? 2 times 2 is 4, but it could also be negative 2. Negative 2 squared is also positive 4, right? Negative 2 times negative 2 would also give me positive 4. So whenever we're the ones taking the square root, right, which we were here, okay, we have to keep in mind that it could be the positive or the negative option, so to speak. So y equals plus or minus root x. Okay. And then lastly, f of x equals x squared minus 4. Well, once again, this is just y equals x squared minus 4. To take the inverse, switch x and y. So x equals y squared minus 4. And now we're just going to go ahead and isolate y, again, just performing the opposite operations or the inverse operations of whatever's happening to y in order to isolate it. So y is being squared, it's having 4 subtracted. Reverse order of operations tells me that first I've got to deal with additions and subtractions. So let me add 4. X plus 4 equals y squared. And now all that's left to deal with is that exponent, right? It's being squared. And the inverse operation of squaring is square rooting. So that will undo or cancel out that squaring. And we get that y equals, again, be careful, plus or minus the square root of x plus 4. Right? Again, the way to think of it is if I know that x squared equals 4, let's say, and I want to figure out what x could be, right? If I show up and I take the square root of both sides to figure that out, that's fine, but I have to realize that x could be 2 or negative 2, right? Both of those squared would mean that x squared equals 4, right? So that's what's going on there. Okay, so there is the inverse of that relation. So go ahead and try these ones out. See if you can come up with the inverses of these functions, okay? Now again, your final form might not look exactly like these. You can see I've chosen to personally write it in the form, since both of these end up being lines, y equals mx plus b. That's just kind of a force of habit, because whenever we have the equation of a line, this is such a nice way to write the equation, especially if we want to graph it, because we see the slope, we see the y-intercept, okay? But swap x and y, isolate y, right? And if you like, you can do what I did and write it in its final form in y equals mx plus b format. All right, so go ahead, give those one a shot. And if you're feeling like you need a little more practice with that before you move on, go ahead and you can try some of the surrounding questions that are similar. And then we will move on. All right, so in this next example here, they want us to, well, they're giving us the graph of y equals 1/2 x plus 2, right? A line with a slope of, a rise over run ratio of 1/2, runs 2 every time it rises 1, and a y-intercept of 2. We can see from the equation, if x is 0, y should just be 2. Sure enough, y-intercept of 2, okay? Now it wants us to draw the graph of the inverse function. Once again, folks, don't get thrown off by the fact they gave us a graph. In fact, be very grateful when you get a graph. It's actually really nice, right? Like when we're doing operations, because now they're just showing us a bunch of places, x and y's, right? We just want to switch those x's and y's. So if I take a look at this, it wants us to draw the graph of the inverse function. So let's just pick out, some points. Here is the point when x is 4, y is 4. I'll just pick some nice easy points where I don't have to estimate. 2, 3, right? When x is 2, y is 3, 0, 2, -2 for x and 1 for y there, and -4, 0 for x, y there. Okay, so to start graphing the inverse of this function, what are we going to do? Well, let's start here. If the point -4, 0 is on the original, then swap x and y, and 0 for x, -4 for y will be a point on my inverse graph, right? Notice literally just switching the x and the y coordinates, right? Taking the inverse. -2, 1 is going to become 1, -2. 1, -2. Okay, moving along. 0, 2, what's that going to become? You got it. 2, 0. 2, 3 will become 3, 2. And 4, 4. What's going to happen to that? Well, if I swap x and y, what do I get? I get 4, 4. Do you remember what we might call a point like that? It didn't move. We took the inverse. We did take the inverse, but the point, that specific point didn't move. That is an invariant point. So that leads into the next thing they asked us here. Whoops, I didn't finish drawing this graph though, because I should connect it. Of course, should use a ruler, but the ruler doesn't work very well on the iPad, so my apologies for the crookedness of this line. It's not terrible, but should use a ruler. I didn't. Okay, but there we go. There is the inverse of y equals 1/2 x plus 2. Okay, all I did was swap the x and y coordinates for all the points I could see. Okay, so what are the invariant points? 4, 4 was invariant. 4, 4 was invariant. And again, that makes sense because x equaled y there, right? Y equaled x. So swapping those two is not going to change that point, right? If I switch these around, you wouldn't even be able to tell. So an invariant point wherever y equaled x, because that's all that the inverse does. All right, now we're going to get into what we mentioned earlier about the idea of reflections in the line y equals x. To see what's going on here, okay, it's asking us to draw the line y equals x. So, like any equation, right, like any equation for a function, right? I mean, again, what is this one showing us? What are these points? They're all the places where the y value is equal to half of the x value plus 2, right? That's all we're seeing there, half of the x value plus 2. So the line y equals x is just going to show us all the places where, well, y is just equal to x. So for example, 0, 0, right? 0 is equal to 0. 1, 1. 1 is equal to 1. 2, 2. 3, 3. 4, 4. 5, 5. And then going the other way, -1, -1. -2, -2. -3, -4, -4. And -5, -5. Right? And if I connect those with a straight line, what I'm looking at is the graph of the line y equals x. I actually might do it with a dotted line here. There we go. Okay, that is the line y equals x. It's everywhere where the y value equals the x value. Now, can you kind of see how this is a reflection, right? Note that every point is kind of equidistant to the line y equals x for its, partner, its corresponding point on the inverse graph, right? That is an equal distance away from the line y equals x. -4, 0 has just been reflected straight across this line. If you kind of turn your head a little bit sideways, it can be even easier to see, right? Same thing for these corresponding points. Or these ones. Or these ones. They're all equally distant from the line y equals x. Just like when you look in the mirror and see your reflection appears to be just as far away, into the mirror as you are out of the mirror. Okay, so same idea here. It's a reflection. And look at this. the point 44 was on the line y equals x. That makes sense because y equals x there, right? So that's why 4 is on that line. It intersects with that line, right? So if we were to reflect it across that line, it wouldn't go anywhere. It would stay invariant. It's already on that line. You can't reflect, I mean, you are reflecting it across it, but it doesn't go anywhere because it's already sitting on the line there, okay? And you can see here that in order to do this, in order to take the inverse, right? If I think about what I need to do to the point 0, 2, to turn it into the point 20, well, I have to take the x and make it 2, and the y and make it 0. And you can kind of see that what that always ends up resulting in is I go from here, to the line y equals x, and then down by 2 in this case, right? Giving me this effect of reflection across the line y equals x. If we reflect a graph across the line y equals x, we always just end up swapping the y and the x values, right? Or vice versa. If we swap the y and x values, we end up reflecting the graph across the line y equals x. So just putting that down in words here, what we kind of just talked about, right? What do we notice about the two functions? The inverse function is just a reflection of the original function across this line, y equals x, okay? Again, like we pointed out, y equals x is just equidistant between any two corresponding points, right? Now, these are just the nice points that we could see the numbers of easily, but it works even at the, the kind of decimal value ones where it's not clear, nice integer numbers. Even there, right, this has a corresponding point that's just reflected across that line, y equals x. And that's going to be the case for whenever we take the inverse of a function and graph it. It'll look like a reflection in the line y equals x, because it is, in fact, that. So trying this next one out here, also giving us a graph, this time, though, giving us the graph of two functions, f and g, and asking us to answer the following questions. So, do the functions share an inverse relationship? And explain. That's an important word in math, right? Explain. It's something you can see on your diploma. It has an important definition. I think the official Alberta education definition is make clear what is not immediately obvious, right? Show something that, think of it like, could you, if you read your explanation, would you understand it if you were a new Math 30 student, right? Explain it like you were teaching somebody else, okay? So do the functions share an inverse relationship? Well, what are the things we should check for to see if it's an inverse relationship? What would we expect? We would expect that for one of them, now we don't know which one is the inverse of which, right? Is f maybe an inverse of g, or is g an inverse of f? That being said, they're inverses of each other, right? I mean, we know that we took the inverse of f here, or the red one, I guess, to get the blue one. But just as easily, we could say that the red one is the inverse of the blue one, right? It's kind of a two-way street, so to speak. But are they inverses of each other? What would we expect to see? We would expect to see the x and the y values swapped, right? So for every point on f, is there a point on g that's, same numbers but switched for x and y? Let's just see. Can we try one out? How about this one? How about the point 2? What would we expect to see on g if this really were the inverse of f? We would expect it to have the point 2, 0, right? X being 2, y being 0. Aha! I do see that there. 2, 0. Okay, that's a good sign, right? Let's try a couple more. What about, I see -1, 0. So g should have 0, -1. Sure enough, it does. Okay. This is actually a pretty good clue as well, right? Wouldn't always necessarily work out, but -2, -2, and -2, -2, right? They both pass through that. So it would be an invariant point if we were to go from f to g or from g to f, right? A couple more. -4, -3 is on g. -4, -3. Sure enough, -3, -4 is on f, right? I mean, only really one left to look at here that at least is, not halfway and is easy to see the numbers for. 1, 4, and 4, 1. So do they share an inverse relationship? I definitely think so, right? I would say yes, they certainly do, because look, every single point we checked, right, there's a corresponding reversed point on the other graph, right? You can find for every point on F, you can map onto a point on G where the X and Y values for that point on F have been swapped, right? Y has become X when we go between these two. So do the inverse functions share an inverse relationship? I would say 100% yes, they do, right? So yes, they do. Now, that is not an answer to this question because they asked us to explain, right? So yes, they do, but now we've got to, if you were a new Math 30 student, would you be like, okay, got it, I understand now? No, right? We need to explain. We need to make clear what is not immediately obvious. So we can see that each point xy on the function f, right, corresponds to a point on G with those x, y values swapped, right? For going from F to G, we're basically doing this, right? Or vice versa. Again, we don't know necessarily which was the original, so to speak, right? This is what the inverse of a relation does to points, right? And I think there we've made it clear why we can say these are the inverse relations of each other, right? We've explained what we looked for to say yes, right? In order to be able to say yes, we explained what we saw that told us yes. We also explained what that means, what the inverse of a relation actually does, right? We could also add here, they did not leave myself enough room here. They are reflections of each other in the line y equals x, right? If I draw in the line y equals x, which is just everywhere where the y value is the same as the x value, right? Notice they are reflections of each other, right? Pick a point. It has an equidistant point on the other side of that line y equals x. It's been reflected across that line. Okay, now it wants us to determine the domain and range of f. Okay, well, look at f. Domain is the set of all x values that can go into the function. And graphically, we can think of that as the x values that the graph will pass through, right? Well, we can see f, the blue one, it starts, quote unquote, at x being -3, and it ends when x is 1. Right? Notice no arrows here. We're clearly shown that it does not extend beyond x being 1 or x being -3. Okay? So, domain, we just got to read it off. Domain for f, okay, the domain is the set of all x's such that -3 is less than or equal to x, which is less than or equal to +1. And x is an element of the real numbers. Right? Alternatively, you could say in interval notation from -3 to 1. Square brackets because we can see it does pass, like it does get to -3 and it does get to 1, but it doesn't go beyond them. So they're included in the domain, but they are the end of the domain. The range for f, I'm going to write small here because I'm running out of room because I leaked into this question with my previous question. The range, well, same idea, except now for y values, right? Looks like it goes as low as -4 and as high as +4, but no higher and no lower. So the y values that our graph passes through for f are -4, less than or equal to y, less than or equal to +4. And y is also an element of the real numbers. Again, saying it's an element of the real numbers is just confirming that it can be a decimal, a fraction, anything, any real number, as long as it's between -4 and 4. Okay, what about G? Same idea for G. Might have to work sideways here a bit. My domain for G is going to be the set of all x's such that, what does G do? It goes from x being -4 all the way up to x being +4. Sound familiar to something we just talked about? -4. Oh, I was supposed to write this down here. I was like, there's not enough room. There would have been enough room if I noticed this was supposed to go down here. G. Okay. Domain, values of all x such that -4 is less than or equal to x, which is less than or equal to +4. And x can be any real number as long as it's in between those ones. Okay. The range, all values of y such that, well, look, what's our lowest y value? -3. What's the highest y value? +1. So from -3 up to, whoops, not x, sorry. That should be a y, of course. We're talking range, y values. What did I say? +1. And y is an element of the real numbers, right? Or we could do it in interval notation from -3 up to 1. Inclusive. Okay, now do you notice anything here? And are you shocked by it? Probably shouldn't be too shocked if we think about what a inverse does, right? An inverse swaps x and y. Domain is the set of all valid x's. Range is the set of all valid y's. So notice here, the domain of f has become the range of g. And the range of f is now the domain of g, right? X and y have swapped when we go from the inverse of one graph to another. So it makes sense that the domain and range would be swapped between the two, right? So that's what it asks us here in D. Compare the domain and the range for f and g. And is that what we would expect? Well, personally, I would say yes, that is what we would expect, right? I wrote this out here. The domain and the range have swapped places for f and g, right? Domain of one is the range of the other and vice versa. The domain of f is the range of g and the range of f is the domain of g. And it makes sense, right? It is what we would expect, because if f and g are inverses of each other, which we've established earlier they do appear to be, then y and x are essentially swapped between them. So it makes sense that domain, which are the valid x inputs, and the range, which are the valid y outputs that we could get out of the function, would be swapped, right? We've swapped x and y. So the domain, x's, and the range, y's, should just be switched around. So moving on to one here from a diploma. So again, a released question that was actually written by students on the diploma. They're saying the graph of y equals f of x is shown below. Often helpful to read the stem first, the actual question first, before looking at the information. So it can sometimes be very helpful in sorting through what's actually important here. So the number of points that would be invariant, remember that means they won't change, when the graph of y equals f of x is reflected in the line y equals x. Okay, so that just means, right, we're taking the inverse. We're finding the inverse. Okay, switching y and x to go from whatever this function is to go to its inverse. We're going to be essentially swapping its y values and its x values, right, to graph the new inverse function, or inverse relation, I should say. The number of points that would be invariant, well, what's going to be invariant? What's going to be invariant when we swap y and x, or when we reflect in the line y equals x? Points where y is x, right? Points where y equals x. That's where we're going to see invariant, because again, if we're at the point 1, 1, for example, switching the x and the y is still just going to give us 1, 1. Okay, well, I mean, we could look at this and try and figure out, does y equal x there? Not quite. X is a little bigger than y. But why don't we just take advantage of the fact that we know that taking the inverse is reflecting in the line y equals x, right? Or more generally even, we know that the line y equals x, what does it show us? It shows us every point where the y value is equal to the x value. Isn't that exactly what we just said we needed to find? We need to find the points on our graph where y equals x, right? So why don't we just, do our best to draw in the line y equals x and see how many points on our graph, the graph of our function f of x, are on that line, right? Because if they're not on that line, if they're not on the line y equals x, then that point will not be invariant, because at that point the y value does not equal the x value, right? This line shows us everywhere where the y value equals the x value. So here on our graph, y equals x, because it's on the line y equals x. Here on our graph, y equals x, because it's on the line y equals x, right? Yes, it's on our graph, but it's also intersecting with the line y equals x. So I see, when I draw in that line, I see two invariant points, right? Two invariant points, two places where y already equals x. And we can tell, this is never going to intersect with this again. This is headed downwards now to negative infinity. This is headed up to positive infinity. No way those are ever going to cross again. And similar story here, although maybe a little less obvious. This one is headed down to negative infinity, and so is our function f. However, you can kind of tell the slope of this one is curving to become steeper and steeper. This is just a line. Its slope is going to stay the same, so there's no reason they would ever intersect again. So, looks like we've got two invariant points, B. So go ahead and give this one a shot now, okay? It asks you to sketch the graph of the inverse function based on the graph of the given function. Again, you can always check my solutions in the filled-in notes to these specific practice questions. And you can always try out a few more as well right now if you want to pause and stop, or if you're feeling okay, you can always come back to those later once you've done the whole lesson. But again, take a minute to practice while it's fresh in your brain. See if you can sketch the line, sketch the inverse of y equals f of x. All right, so here's where we're going to circle back to the idea of functions versus relations, and what I've been kind of alluding to about how sometimes with these inverse things, we sometimes want to make sure that the inverse is a function, or at least check if it will be a function. And that's where we can make use of a horizontal line test, right? Why a horizontal line test? Well, remember, any function should pass the vertical line test, because a vertical line drawn anywhere should intersect with the graph of a function only once. It's not some magic trick. What we're doing by drawing a vertical line is examining each value of x. Wherever we draw the vertical line, we're just examining that value of x. If it intersects with our graph more than once, anywhere, that means at that value of x, there's more than one value of y being output. So it's not a function, right? Can't be, okay? But sometimes, as we've seen in some of the previous examples, right, some of the ones we've looked at, we might not have talked about it, but we saw some that weren't exactly functions themselves. The inverse of a function might not itself be a function. And it works the other way too. Sometimes the inverse of a non-function could end up being a function, right? You might take the inverse of a non-function and get a function. We could absolutely graph the inverse function, right? Given a function, we could graph the inverse and then do the vertical line test on it. But there's a faster way. If we think about what an inverse does, taking the inverse does, what it does is it swaps x values for y values and y values for x values. And if you think about what that means, it's effectively swapping vertical, y, and horizontal, x. Or another way to think about it, if I want to check, an x value, I draw a vertical line. But what if I want to check a y value that's about to become an x value when I take the inverse, right? Well, to check a y value because it's about to become an x value when I take the inverse, to check a y value, I would need a horizontal line, right? Now, if I drew that, I'm examining y equals 3, assuming this axis is scaled by 1, right? So that's the idea here. I want to examine, if I want to know if the inverse of this thing, not this thing, but the inverse of this function is going to be, I shouldn't call this one a function because it's not, but if I want to know if the inverse of this relation will be a function, what I actually need to examine are the y values with a horizontal line. Because those y values, when I take the inverse, will become the x values, which is what I would then check on the inverse to see if that inverse is a function. So I can cut out the step of actually graphing it by just saying, well, let me just check these y's and see if I took the inverse, would the inverse pass a vertical line test? So I could do that by just cutting out that middle part and just doing a horizontal line test. So we can therefore predict whether the inverse of a relation will be a function making use of a horizontal line test. And that saves us from having to graph it. Don't get me wrong, graphing is fun, of course, but sometimes, we're short on time. So we can apply this test to the original relation without ever graphing the inverse relation in order to determine whether the inverse relation would be a function or not. So that's the horizontal line function, right? Horizontal line test. If a horizontal line drawn anywhere intersects with the graph of a function only once, or once at most, then the inverse of that relation will be a function, okay? So for this example here, is the original relation a function? And then will the inverse be a function? All right, well, first up, is this original? Is that a function? I can use a vertical line test. No, right? We can see original, not a function. Original, not a function. It's a relation. There is a relation between x and y, but it's not a function. One x is clearly giving us more than one y, pretty much no matter where we look. Okay, but would the inverse of this be a function? Well, if I were to draw a horizontal line anywhere, right? If I draw a horizontal line anywhere, it looks like we're only getting one intersection. So if I took the inverse of this, right, what would I end up with? The original is not a function, but the inverse would be a function. Is a function. All right. Taking a look at this one here, is the original a function? Let's see. Vertical line, only one intersection. Vertical line, only one intersection. Vertical line, only one intersection, right? No matter where we imagine drawing a vertical line, I'm only seeing one intersection. So the original here, the original is a function. The inverse, on the other hand, right? Be careful. Make sure you imagine it in more than one spot, right? Don't just say, yep, I could draw a horizontal line there, right? It's not about just for one specific value. It's for all of them, anywhere. So sure enough, if I drew a horizontal line there, it would intersect with my graph, not even twice, 3 times, right? One value of y is associated with 3 different values of x, okay? Now that's okay for the original to still be a function, but once I take the inverse, think about what that's going to mean. It's going to mean 3 values of y on the inverse are associated with 1 value of x, because again, the inverse is going to swap our x and y. So at 1 y value, we are associating with 3 x's. On the inverse, that means on 1x, we're going to be associated with 3 y's. So the inverse, definitely not a function. All right. One more here. Is the original a function? I don't like the look of this, right? I'm sure you can picture a line. Nope, not a function. Original, not a function. But the inverse looks a little more promising, right? Horizontal line. Okay, only one intersection, right? Only one intersection. Examining this value of y, which will become a value of x when I take the inverse. Only one intersection. So the inverse looks to be a function, right? I see one intersection, one intersection, one intersection. So the inverse is a function, or will be, I guess you could say, because we haven't actually taken the inverse here. We're thinking about, would it be a function? All right, so vertical line test to test if the original is a function, and we can just do a horizontal line test to test if the inverse would be a function. Even if we don't go to all the trouble of graphing it, we can still work that out using our horizontal line test. Because again, we swap y and x. We swap vertical and horizontal. So I've just quickly put some stuff into Desmos here. Now, normally I would encourage you to graph anything on your graphing calculator so you can get used to it and not use Desmos. But Desmos is a handy tool for, it's got nice colors and it makes things pretty quick. So not something you're not allowed to use at all. But again, I would encourage you to use your graphing calculator whenever possible. But I put it into Desmos here. I just put in two functions. In red there, you can see on the left, I've got y equals x squared, right? In blue, I've got x equals y squared, and then in green, I've got the line y equals x, right? And so you can see here, like if we look at y equals x squared, and then reflecting it across the line y equals x, in other words, finding its inverse, right? We end up with this, which is no longer, this is not a function, right? We can see at one x value, there is almost everywhere we look, that's greater than x being 0, we get two outputs, right? Now again, Desmos lets us put in this x equals y squared stuff. Our calculator would require us to solve for y if we wanted to graph it, and we'd have y equals plus or minus the square root of x, right? So then at one x input, we're getting two y outputs. For example, if y equals plus or minus the square root of x, then when x is 1, for example, y could be 1 or negative 1. In fact, we see those points on our graph, right? 1 and then negative 1 down here, okay? So just wanted to show you that visual, right? It makes sense when we reflect stuff in the lines y equals x, it's possible to turn them into, it was a function and now it's not. And by the way, this isn't always the case. For example, if I do y equals, 2x, and then I think about the inverse, x equals 2y, which we could solve for y to get that y equals x over 2, right? And if I graph those, they are inverses of each other, but notice these are actually both functions. So it depends on the nature of the function, right? A linear function's inverse will pretty much always also itself be a function, okay? But it's that reflection across the line y equals x that I think gives some more context as to why we can have something that was a function not be a function, or its inverse is not a function, right? Or when we take something that wasn't a function, a relation that was not a function, and its inverse ends up being a function. All right, so heading back to the notes here, let's try this one out. A partial graph of y equals f of x, where f of x equals x squared plus 2x minus 3 is shown on the coordinate plane. There it is, right here. Draw the graph of x equals f of y. So remember, that's just one of the few ways that we can represent taking the inverse, right? Finding the inverse relation or function. In this case, we can tell, I'll quiz you, will the inverse of this be a function? No, right? We can tell, a couple ways. This would fail the horizontal line test. Its inverse will not be a function. We can also kind of picture what it's going to look like when we reflect it in the line y equals x, right? That's going to take this parabola and end up kind of making it into like a sideways parabola, right? And a sideways parabola won't pass the vertical line test, so we can predict that the inverse of this should not be a function. But let's go ahead and sketch the inverse. Basically, we've done this already, but now we're doing it with a parabola for a quadratic function as opposed to a line for a linear function. So we'll just take some points, right? Here's the point 2, 5. That tells me that on my inverse function, or inverse relation, I should say, it's not going to be a function, we just said, I should have the point 5, 2. Okay, just looking for good points, right? Trying not to, if I don't have to, don't want to estimate too much. So there's the point, what is that? That's going to be at 1, 0. So I should expect on the inverse relation to have the point 0, 1. Okay, we can actually already tell too that this point right there, that will be on the inverse. How did I know that? Because, look, it goes through the line y equals x. That's an invariant point, right? I don't know exactly what its value is. Maybe it's 1.3 or 1.25. Who knows, right? For sure. But I do know that that point will also be on the inverse relations graph because it's on the line y equals x. So that will be invariant. I mean, while we're here, we could even do that point. That one down there will also be on the graph. Okay, let's just get a couple more. So I see, there's a nice one I don't have to estimate for. 0, -3. So I should see -3, 0. Now, that still is an invariant point. Or sorry, that is not an invariant point, right? It did move. I know it got moved to somewhere where our original graph happened to be, but this point did get moved to over here, right? It has to just stay in the same spot to be invariant. So this is a variant point. It got moved from here to here. Okay, that place just happened to also be a point where our graph of f passed through. All right, continuing on here, how about -1, -4? That will have a point on our inverse of -4, -1, right around there. And this is the vertex of our original parabola, right? So this is going to kind of be the vertex of our sideways parabola here, right? Although kind of strange to call it a vertex because that's where it changes directions on the y-axis, but similar idea. Here's a good one, -2, -3. -2, -3. Where will that end up? Well, -3, -2. -3, -2. And notice again how all of these look like reflections in the line y equals x, because they are reflections in the line y equals x, right? Every point on the inverse has an equidistant point, its corresponding point on the original. All right, any more we can get here? How about -4, 5? Where's that going to end up? Well, at 5, -4. Right there. Okay, and I think with that, we have a pretty good idea of what the shape of this graph is going to be. So I'm just going to kind of do my best to smoothly connect them. Something like that, right? Something like that. Okay, so there we go. We graphed the inverse relation of our original function. Okay, then it asks us to compare the x and y intercepts of f and its inverse. And it asks us, what do we notice? Well, let's see here. What do we notice? First of all, let's find the x-intercepts of f and the y-intercepts of f. So it has an x-intercept at... has two, actually. It's got an x-intercept at, looks like -3, 0. And 1, 0, right? That's where it crosses the x-axis, two places, -3 and 1. Where's its y-intercept? Well, where does it cross the y-axis? Looks like it happens at 0, -3. Okay, what about our inverse? Well, it's got, hey, look at this. It's got one x-intercept and two y-intercepts. That kind of checks out, right? I didn't do a very good job of drawing this, I'm seeing now. It should be passing through that point. There we go. It's a little better. Okay. So this had two x-intercepts and one y-intercept, and we can see the inverse has one x and two y-intercepts. It kind of makes sense when we think about what an inverse is, right? Let's just finish up writing them out. X-intercepts at, well, just one x-intercept at -3, 0. Notice anything, right? Does that make sense? Why that would be the case? Why the x-intercept for our inverse would just be where the y-intercept was, but of course with the x and the y switched, right? And its y-intercepts, it has two now. It has two. It has one at, whoops, I don't know why I switched colors there. That should still be blue. We're still talking about the inverse. It has two. It's got one at 0, 1 and one at 0, negative 3. One at 0, negative 3. Oh boy. Just realized I was writing that in the wrong spot. Sorry, folks. Okay, so 0, 1 and 0, negative 3. There we go. Okay, and again, compare. Right? Compare. The old x-intercepts have become the new y-intercepts. Of course, with the x and y values swapped, otherwise they wouldn't still be y-intercepts, right? Or x-intercepts, but we can see there, negative 3, 0, 0, negative 3, right? That makes sense. Wherever the x-coordinate is 0 on the original function, well, on the new function, the y-coordinate will be 0. And wherever the y-coordinate is 0 on the new function, the x-coordinate will be 0. And wherever the y-coordinate is 0, that's just an x-intercept, right? Wherever the x-coordinate is 0, that's just a y-intercept. So switching them around just turns an x-intercept into a y-intercept, and vice versa. So this one, we already talked about it, right? Is the inverse a function? No, I mean, we can tell we've graphed it, so we can tell it fails the vertical line test. And technically, we said it before we ever even graphed it, right? We said that the original fails a horizontal line test. So its inverse will not be a function, right? Horizontal line test is examining each y value and seeing if there's more than one x associated with it. So when we take the inverse, that means we're examining the inverse's x value and seeing if there's going to be more than one y value associated with that. So no, the inverse is definitely not a function. Okay, so could say something like that, right? No, it fails the vertical line test. We can see that one input, x, gives more than one output, y, in many cases, right? Just for a couple examples, x equals 0 has y equals 1 and y equals negative 3. One input, x being 0, is leading to more than one output. Could also add here that we could have told this before ever graphing anything because the original fails a horizontal line test, which leads us nicely into this next question here. And this is something we sometimes want to do, is we might know that the inverse is not going to be a function, right? Like this one. We knew the inverse was not going to be a function because it fails a horizontal line test. But if we restrict it to just certain values of x, we might recognize that on the whole domain, for x being all real numbers, yes, the inverse of this will not be a function. But what if we just said, as long as we keep x to certain values, then the inverse of f could itself be a function, right? What if we say, yes, the inverse of f for all values of x might not be a function, but for certain values of x on certain domains, it could be a function, okay? That's what we're talking about here. State two possible restrictions that could be placed on y equals f of x's domain so that the graph of its inverse would represent a function, okay? So again, just to think about that, what would we need? What would we need y equals f of x to do so that its inverse would be a function? Well, to make the inverse of y equals f of x be a function, y equals f of x would need to pass a horizontal line test, right? And right now, again, it does not. If I do a quick sketch of y equals f of x, the red one there, right? It's got a vertex down here at -1, -4, and this is not going to be a perfect sketch by any stretch of the imagination, but it looks something like that, right? And no, this is not going to pass a horizontal line test, so the inverse of f is not a function. However, what if we limited the values of x, right? We might say the inverse of the function f is a function on this specific domain. Because, for example, wouldn't this, half of the graph, wouldn't that pass a horizontal line test? What if I said as long as we keep x greater than -1, right? Well, then that part, just the highlighted part, a horizontal line is never going to intersect with that more than once. So that's one restriction we could absolutely do, right? We could just say, well, as long as x is greater than -1, the inverse of this could be a function, right? So if we restricted the domain, right, if we restricted domain to x greater than or equal to -1, then inverse of f of x would be a function, right? It would pass the horizontal, the original would pass the horizontal line test on that domain, right? So we could say inverse of f of x is a function for domain the set of all x's such that x is greater than or equal to -1. That's definitely one that would get it done. Do you see another thing we could do? Right? What about this half? What would be my restriction that would give me that, right? That would also pass a horizontal line test. This is my original function. I can tell that the inverse just for that half of it could be a function, right? So thinking of that then, right? Or, and very important, or, not and, okay? Or if x is less than or equal to -1. Okay, that's another restriction that we could use. In fact, what we're actually looking at here, and when we talk about radical functions, you'll see it a bit more. Remember when we do like, y equals x squared? If I find the inverse, x equals y squared, then I square root both sides, but I keep in mind that there's a positive and a negative option. What you're actually seeing there, essentially by restricting it to one or the other, basically what we're doing, obviously it's not the same exact function, I'm just doing y equals x squared, but there's like a positive one, that's y equals positive root x, and you can see that's a function, right? And then there's like a negative one, that's like this, that's y equals negative root x. Notice, put those two together, what do you get? You get a sideways parabola, right? That's where you get the inverse there. So individually, those are functions, right? That is a function, that is a function. And this is just one half, so to speak, of the parabola having had its inverse taken, right? Or same thing here, okay? So it's not always a parabola necessarily, but that's the general idea. If you want to restrict the domain so that the inverse will be a function, you basically just need to find, is there a section of this graph, right? If x is greater than this value or less than this value, is there a section of it that might pass the horizontal line test, even if obviously the whole graph never would, right? For all values of x, this won't be the inverse won't be a function. But if we keep x less than -1, these values, these points, right, give us a graph that would pass the horizontal line test and therefore have an inverse, which was itself a function. Okay, so that actually wraps up the examples in the notes for lesson 3 of unit 1. So go ahead and do your practice. You can start with this one while we've just been talking about it and it's fresh in your brain, and then you can do the rest of your practice. Make sure, as always, you're reaching out for help or for questions or whatever it might be. And this actually brings you up to the end of the material that is covered in the Topic 1, Unit 1, Topic 1 quiz. So when you're comfortable with the material, you've done your practice, you are free to do that one. Do that quiz. All right.